So in this video, we're going to discuss entropy. Now, when you start to learn about entropy in physics, you learn all sorts of different definitions, and you realize there's all sorts of different ways that one can think about the entropy of a system. So to start this video, I thought I would start by giving you a few of the ways that you can think about entropy. So one of the ways is thinking about it in terms of microstates and macrostates. So the first way is entropy tells you about the number of microstates associated with a given macrostate. Period. So if you have a certain macrostate and you want to compute its entropy, it's going to tell you how many microstates are associated with that. And so really it's just a function. So the entropy is often denoted by the letter S. And by this definition, it's given by Boltzmann's constant, which again, right, this is just a constant out in front to get the units right, times the natural log of, let's call it omega, which is the number of microstates. So this is just a function, so you could always invert it and say if you have a state with some entropy, you know the entropy, then from that you could compute the number of microstates that are associated with that macrostate. So that's one way you could think about entropy. So the second way is thinking about it as a measure of disorder. And maybe it's best to wait until we're about to see an example to think about what we really mean by this measure of disorder. And then the third definition, I'll write right here for space, is it's a measure of lack of information. And this is really directly correlated to this microstate-macrostate relationship. So if you only know the macrostate of the system, if a given macrostate has lots and lots of microstates associated with it, then that means if you only know which macrostate you're in, then you really don't know. I mean, there's a lot of information you don't know because there are many potential microstates you could be in. So this relationship really tells you that entropy is also sort of a measure of your lack of information. If you only know that which macrostate you're in, but you don't know which microstate, then your entropy is telling you how much information you're missing by only knowing the macrostate. So to understand these things a little bit better, I thought that it would be nice to think about a particular example. So let's think about the change in entropy, Entropy, in free expansion. All right, so let's consider, what I mean by this is, let's consider some box that is divided in half. So we have some volume on one side, some volume on the other. And let's say initially we have some ideal gas that's all contained on one side of the box. There's some partition here that's keeping all of the particles on one side of the box. And then what we're going to do is we're going to remove this partition. We're just going to, suddenly make it vanish, and then sometime later, our box, now the partition is gone, the volume is twice the volume, and now we expect the particles are going to sort of spread throughout. They're going to freely expand into the rest of the box. All right, So let's think about the entropy of each of these states. So what we want to do is we want to compute the change in entropy in going from the state where all of the particles are on one side to the state where they've been allowed to freely expand throughout the entire 2V volume. Okay, so we have our expression for the entropy right here in terms of the number of microstates. So let's start by saying, okay, how many microstates do we have in this situation? So let's say that, so we don't really know, but let's say each particle can be in X states. So this could be like, let's say there are X different places each particle could potentially be on only this half of the box. There are X different possibilities for each particle. So then, what are the total number of states? So if we have, let's say, N particles, then the total number of states is X to the N, right? Because you have to multiply the X states of each particle by each other. So X times X times X N times to get the total number of possible states. And then that tells us, we can just plug this now into our entropy expression, that the entropy, the initial entropy, so the entropy of this state, again, the entropy is a well-defined property of a particular state. The entropy of the initial state is Boltzmann's constant times the natural log of this total number of microstates. So again, knowing each of the positions of the particle, for instance, this is a microstate, the total number of microstates in this given macrostate, where the macrostate is just saying that we're just saying the macrostate of all the particles being on one half of the box. So then we remove the partition, let the gas freely expand, and now we want to know the entropy of this final state. So now each particle, it's not only X states, right? Now there are twice as many locations for the particle to be in. So now each particle can be in 2X states. So there are twice as many options for locations of each particle. So now they have 2X options instead of just X options. And then again, the total number of states is equal to each of the N particles. Again, we still just have N particles is equal to now 2X to the N. Again, it's 2X times 2X times 2X for each particle all the way up N times. And so the final entropy is equal to KB times the natural log of now 2X to the N. And so what we wanted to do is we wanted to compute the change in entropy and going from this initial state to this final state. So the change in entropy is equal to the final minus the initial, which now we can just plug these in. Maybe let's pull out Boltzmann's constant in front times the natural log of 2X to the N minus the natural log of X to the N. And then if you remember your properties of natural logarithms, then we can combine these. This is the natural log of 2X over X to the N. And so the X's cancel, which is good because we didn't know that information anyway. And so then we end up with Boltzmann's constant times the natural log of 2 to the N, which again, remembering your properties of logs, when you have an exponent like this, the N actually can be pulled out in front. So it's KB N natural log of 2. So what we found is that there was some increase in entropy in going from our initial state where all of the particles were on one side to our final state where now the particles can be anywhere in twice the volume. So let's think about how this fact can be interpreted sort of in our 3 different definitions of entropy. So the first one is sort of automatic, right? It tells you about the number of microstates associated with a given macrostate. So in this final state, there are more locations for the particles to be in. There are more microstates associated with the macrostate of having the particles spread throughout. Whereas on this side, because the particles were constrained, the macrostate was that particles were only on half of the box. That was our macrostate. That means there are fewer microstates because there are fewer possible places for the particles to be in. So because we saw an increase in entropy, this is associated with the fact that we had an increase in the possible microstates associated with the particular macrostate. So hopefully that one was pretty clear. So the second one is that it tells you about the measure of disorder. And so this is always sort of a vague thing to think about. But I mean, so in a sense, what I mean by disorder, maybe you can see now, is that this state is said to have less disorder than this state. This is sort of ordered, right? Everything is pushed to one side. There's sort of some order here, whereas here, everything's all over the place, right? If you were talking about whether your room is clean, whether your bedroom is disordered or not, when it's all disordered and messy, all of your clothes are all over the floor. It just looks like there's an explosion and everything's all over the place. Whereas when you order your room, when it's in a more ordered state, everything is back up on the shelves and they're very particular locations. So that's more like this state where half of the particles are on one side. So this state is said to be more ordered, whereas this state is said to be more disordered. So that's the sense in which entropy, because entropy has increased, is sort of a measure of this increase in disorder. And then the final one, again, tells you about your lack of information. And again, this is really sort of exactly the same thing as 1, right? So because each of these particles now, so let's consider this little guy right here. So before, it had to be on this half of the box. And so each particle, you sort of had some information about it. You had the information that it could only be on this side of the box. Whereas now, each individual particle could be on the right half or the left half. You don't know. You don't know that information. So in a sense, in going from this state to the final state, you've lost some information. You've lost, if you wanted to track each individual particle now, you have twice as many places for each particle to be, so you have less information about each individual particle. You have less information about what particular state you're in. So I guess the final thing that I wanted to note about entropy is, so we found that this increase in, or that the change in entropy was a positive quantity, which is a good thing because the second law of thermodynamics, which, like how entropy has many definitions, the second law of thermodynamics has many ways of stating it. One of the ways is that the entropy of the universe is always increasing. So in going naturally from this state to that one, the entropy increased, the entropy of the universe increased, and that is the way of the world. And you might say, okay, well, Alex, couldn't we force these particles back over to this state and then the entropy will have decreased the entropy? What about that? Well, in order to get the particles to go back, so we'd have to take a partition and push them back over, we'd have to do some work. And in doing that, if I did that physically, I'd be using energy, I'd be creating heat. And so if we really consider everything that's going on, if we consider me as a part of the system, then the total entropy of everything will have increased. So the entropy of, by pushing a partition over, the entropy of this particular system, the subsystem, will have decreased, but the entropy of the universe will have still increased. So hopefully that clears up some things about entropy and different ways that you could think about entropy and particular ways you could compute entropy for certain states. So thanks for watching.